The stuff I'm going to do today is stuff which is all examinable, guaranteed some of it will be on the exam, and it makes you a better programmer if you understand it. If you don't understand this stuff, lots of what you do is a mystery. It's not really understood. So that's kind of, in particular, we're going to look at things like, people have asked previously, how do I create something which is like a private variable in C? Or, what does a static word do? How does that work? I'm going to try and answer some of that today. Also, answer some of the stuff about, things like we may not have covered explicitly how header files and that kind of stuff works. So hopefully, in between last week and this week, that might answer some of that stuff. Almost all C programs are going to have multiple files, with the exception of, simple programs. In fact, if you have a look at something like the implementation, you can actually find the implementations for things like printf, or for the Unix program printf, or for ls, and so on. You can find them online, and they're part of the core utils library, and you'll see that most of them are single file, although they've still got some stuff. Although they're not really great examples of well abstracted programs, they're kind of more spaghetti code, unfortunately, which is why I don't normally refer people to them. So we have things to help us to actually, when building a bigger program, and some of those things, such as header files, which we've come across before. Does anyone remember why we have header files? Well, if you look at normal programs, right? Can you imagine if we couldn't have a function prototype? How hard would it be to write a program? So I've got this function called printf, right? But I can't actually write a program including printf until I've defined printf. It then means that we've all got all of this extra bloat everywhere we write, anywhere we write our own code, we've got to include all of this extra bloat of other people's code, which means as well you can't hide the implementation of your functions. Anyone who uses those functions needs the source code. That's not really going to be much use. So instead, you in your header file you define the specifications, and so anywhere that wants to use your library, they only need to know the specifications. They don't need to know the implementation details, because that'll all be linked together by the linker at link time after compilation of all the files is finished. Right? Now, storage classes are various modifications to the behavior of variables and functions, which we're going to have a look at today. Things like extern, static, and various others. And we're also going to have a look at preprocessor directives, particularly for conditional compilation. So, for example, you're trying to write a program that needs more information about the environment it's running in than what's available in ANSI. So, for example, you want to know information about the terminal or about the operating system that you're running on. That stuff cannot be known in a portable way. And so what we do is we have conditional compilation, so hash if def some constant, and that constant is defined for that environment. So for example, there is a constant which is defined on all machines which run Linux, and you can test for that constant, and then you know if it's defined, we're on Linux, that kind of thing. So, okay, you tell me, why write a multi-file program? Why don't we chuck it all into one script, or all into one file? Yeah, it is very hard to manage a single file. Yeah, that's really important, being able to reuse modules. So, for example, if we have a list module, we might want to actually reuse that list in different programs. If it's all in the same file with all the application logic, yeah. Yes, reducing compilation time, that's also important. But also, what's the benefit for you of smaller logical units? But the benefit for you as a human. Yes, but it also means that there's less things you got to keep in your head as well at the one time. Yeah. Yeah. So that's a reasonable list. So as people said, a team of programmers can work on one program, each working on a different file. What kind of software can we use to help make that teamwork a lot easier, even when we're working with people in different countries, different parts, like we're not immediately in human contact? Yeah, well, Git is an example of source control, and I really encourage you, if you're not familiar with source control, to get familiar. I've used Git, and I've also used Subversion. Just write that down. Yeah, well, CVS, which Subversion was based on, I believe was worse. Which CVS stood for Concurrent Versioning System. But, you know, there seems to be something about source control which makes it a hard thing. And it is hard to understand and hard to get right. And has anyone here used... Well, truly, yeah. I mean, it is, but I quite like having it integrated as part of your workflow, which you can do with source control programs. With Trello, is a little bit, it's like a different interface. You've got to move yourself sideways and type stuff into there. It's good for stuff like keeping track of meetings and decisions and all that kind of stuff. but I find the software workflow is yeah. Well, as it is, you can already add items to a Trello board through email, right? So there's no reason why you can't integrate, like, you make a commit and that fires off a script in your Git repository, which sends an email to the Trello board, which adds a card there saying that this commit happened. No reason why you can't do that. Probably be some Git integration going on, which will end up going on, I'm guessing. Anyway, we'll see. And yeah, so each file should in fact essentially encapsulate the behavior of one aspect of the system. That's generally my view of things. My view is that what should be an object in an object-oriented language should in fact be a module in C. So yeah, files can hold all the stuff about a related thing. And sometimes you may, in fact, what is like a class in an object-oriented language may end up being several files. You might want to break it down even further. That's fine. It's important to not overly complicate the structure to the point where you can't really find things. Have any of you heard of Doxygen? Have you used it? Cool. Now, one of the things I like about Doxygen, well, it allows you to create HTML documentation from your source code, and people have used JavaDoc in Java. Anyone done that? Well, it's the same kind of idea. But one of the things that actually Doxygen can do for you is in fact to draw a diagram of the links between this module and other modules. Like a little diagram which appears at the top of the documentation for this module. Which that can be quite handy when you're struggling to kind of visualize the connections and so on. Yeah. And yeah, the whole idea in particular with makefiles is that we only need to rebuild those bits which we've changed. Or as programmers often, like for example the C++ team people like to talk about, you only pay for what you use. Ideally in a programming language that should be the case. You only pay for those things that you've actually changed. So you shouldn't actually have to wait 6 hours to recompile your uber duper super huge program when you've just changed one line in one file. In any program, you might have like you have lots of other files, but you must only have one main. Although I've worked on programs where the underlying data structure for the series of programs is the same. So I made them part of the one project, but they had different make targets. So you would in fact, there'd only be one main in any executable, but there might be more than one main in the project because there are different programs which did different things for me. That's quite common. So yeah, the whole point though is that this multi-file structure should actually facilitate the ease of writing software. So we'll actually write you might divide up, start designing a program by dividing it up into several sections. I find a good place to start, and I can talk from experience because this is what I did with your assignment too, is I started from, okay, I want to write this program. I started off with the idea of a text editor, and I said, well, I want to write this program. So my starting point is, what are the data structures I need for the core functionality? So I start off with the linked list, and then realize, well, I need this line structure. That's probably going to make it a bit easy for me. And there are some bits which I just know I'm going to put into any assignment for this course. So things like utility and main for granted. If it's a menu-driven system, I might have a menu.c&h. So you can see how, from basic ideas about the data structures I need and common elements, I build up what the structure is I need for my program. That's an important skill. Have all of you done software engineering fundamentals? Well, that stuff really is essential. It doesn't really matter whether we're talking about a object-oriented or a procedural programming language. It's all the same stuff. Now, one of probably, for those of you who are used to object-oriented languages, one of the main differences is that object-oriented languages tend to write a lot of code for you. So if you look at a class like in say Java or Python, if you were going to write your own list, that would be a class. Yeah. And so lots of things like memory allocation and so on will be written for you. You just have to write the constructors and the methods. And every method in your class has a hidden parameter. Anyone know what I'm talking about? Every method that belongs to a class in an object-oriented language has a hidden parameter. Correct. Self, this, whatever the word is for the current object. In C, we've got to provide that as a parameter. But that's the main difference. That's, yeah. Otherwise, yeah. Okay. I'm not so familiar with Python, to be honest. I've written a few Python scripts to get the job done, but it's not a language which I've been all that attracted to personally. Neither here nor there. So yeah, what we're really talking about is the kind of data abstraction which we've encouraged in this course. And one thing you're going to find, if you say to people that you're learning C, they'll go, oh, it's really hard to write well abstracted data structures in C. You know, it involves lots of spaghetti code. That's actually not true. The problem is there are a lot of poor C programmers out there. And you can see from the way what the kinds of things I've been encouraging in this course, we can actually move beyond that and actually learn from what's been going on in the object-oriented world, even if we're not doing OO. So yeah, this kind of mimics the fact that, well, you know, for example, a list would be a class in an object-oriented language. In C, we have a struct to define the data structure. Isn't what C++. Yep. C++ is, Java is, Python is. Most modern languages are, because it makes life simpler for the programmer. Although it's not too hard to write that additional stuff, and I move quite happily from object-oriented to procedural programming all the time. Doesn't bother me. And the more flexible you are, the more options you have. That's my view. So yeah, this kind of does refer to kind of more object-oriented languages, but all of this can be done in C. We have a single, what they call a translation unit, or a C and H pair, that perform a single job. And it minimizes where you need to change things. This relates to a concept called coupling. Anyone know what that is, coupling? You may not have come across it yet. Or I guess I would say dependency. So an example of coupling is the line list and the line. There's a coupling between line list and line because we can't have a line list without lines. Yep. Next week I'll show you how we can actually get around that problem and actually have lists which can hold anything. Okay. Okay. So let's start talking about storage classes. Storage classes, they're essentially modifications to how things are stored in C. They're probably they're as close as we get to visibility modifiers in Java. You know, like in Java and C++, there are things like public, private, protected. C++ has the idea of a friend, and so on. Which are various ways to modify the visibility of things. C doesn't have those. It has some other stuff. So here we're going to have a look at these visibility modifiers. So these storage classes. So auto, extern, static, and register. So when we're having this conversation, I want you to have this image in mind of memory. So if we think about down here. So here we've got the stack, right? And the stack grows downwards as we declare new variables, or when we jump into another function, this grows downwards. Then the heap in principle grows upwards. Generally what happens is that we get a page at a time, and a page has some fixed value. You know, like for example, it might be say 8 kilobytes. And so every time we ask for one little bit of memory, if we overrun a page, we get an extra 8 kilobyte page. And when we ask for memory, the system tries to allocate from there first. That's the idea there. And that's the heap memory I'm talking about then. Okay. So now when we're talking about command line arguments, they're up the top here. They're before the top beginning of main, and therefore they're visible everywhere if you've got a pointer to one. Now, when we're going to be talking about static and globals, we're actually talking about stuff which is allocated down here. CPT2 is not actually within the stack frame, and so in principle it's visible anywhere. Does that make sense? This is worthwhile image to come back to, I think. Okay, so anything declared within braces, that is within a function or within a loop or what have you, has a default storage class of auto. And auto means automatically allocated. So they are allocated when we enter that block. And then they are deallocated when we leave that block. So in essence, when we enter a block, any variables declared in that block are allocated at the start. And that's why, for example, you get a compiler warning if you have mixed declarations and code, because in essence all those variables have to be created before any of that code runs anyway. So that's why you get that compiler warning. Does that make sense? Any questions? This is also, by the way, why you can't return the address of a local variable. Is because it is popped either when you leave that block or soon after. It is marked as reclaimable. Yeah. Okay, so then we've got extern. Now, an extern variable is essentially something declared outside of a function. Right? And it has extern class, which means that it is in fact created here before we enter the program. Right? But we don't use extern just for any global variable. Extern means this variable was declared elsewhere. So I might do something, just quickly I'll show you. Like, radio. So in my C file here, it's going to include and what I'm going to do is have int nums 20, right? And over in my header file, what I'm going to do is extern int nums, right? And so what that means is anywhere I include the header file, it will know about this global variable and it can use it quite happily. But there's only one where I actually give it a size, and that's here. So here I'm actually, this is a declaration, this is a definition. And in fact I could even put some values in here. And so on. Right? And so you see this is a definition. This was simply a declaration that there will be something called nums which will be an array. So a global variable that I can use. So that's an example of an extern global variable. And typically I only use these actually for things which are constant. So here, these are a range of values which I might want to reference. A classic example of this is strings, which represent various states of the system. I might in fact have here something like enum states with begin, middle, end. So I like to have an invalid state, or I might even say s underscore so that it's clear this is a state. And then have a global const array of strings which give the string representation of these. Now because it's an array of strings, it has to be an array, and therefore you'd have to do this kind of thing. Okay. So a function is in fact also extern. That it is a global symbol. That's why we can actually call them from anywhere. And technically we probably should have the extern keyword for function prototypes, but they're a well-known thing, so we don't have to do it. So items in extern storage class come into memory at program start. They come into existence first. They exist for the entire lifetime of the program. So they are first thing created and the first thing destroyed. So last thing destroyed. Yeah, that should be last. My bad. Actually, I'll change that. Yeah. Sorry about that. Now, the issue is that with modifiable globals, there's no control over where they're destroyed. Personally, I prefer to keep global variables to have only static globals, not to actually have globals which are global to the entire program unless they're either const or if you need them because you're using a function of the language which requires globals. So for example, if you were going to register the function to free memory using @exit, if we have a look at that, @exit, which accepts a function pointer. But you notice here the function pointer only accepts void as an argument. Therefore, anything which it accesses must actually be global to the scope. Yeah, so global variables should generally be restricted to as smaller context as they can be and only used when necessary, because they open up all kinds of abuses. So we're trying to minimize that. So I wouldn't say they're always dangerous. I mean, I wrote a program just recently where there were certain data structures which were freed automatically at exit using that exit, or registered with that exit. But then they weren't visible in any other function anyway, because the only thing in the main module was a main function and they were static globals, so they couldn't be seen from anywhere else. So the odds of, they can't actually be modified. It's quite common these days in programming courses for you to be told that they're always bad, but there's a lot of programming you can do where you can't avoid them, particularly system programming. If you're wanting to, say, write certain kinds of device drivers and things like that, it really isn't possible to do that work without some global variables. So yeah, because of the interfaces defined in the language for it. So sometimes we want to actually essentially have a variable that lives beyond the function but can't be accessed elsewhere. And that's where the static storage class comes in for locals. So static local variables are located in the same memory segment as globals. So they are created at program start and destroyed when the program ends. But their visibility is only the function in which they are declared. So if we have a brief look at this static exam, so I'll just connect to the servo. So here I've got, if we scroll down a bit, I got this function get next ID, right? So it starts off with ID being 1, and so it returns the value and then increments. So up here I have this here. What we're doing is we're counting, then do get next ID. We're going to print it. So down here I've got this get ID function. But the important thing is this is all driven by this next ID, which is static. And therefore it keeps in memory what its previous value was, but we can only see the value in here. Can't see the value elsewhere. But up the top here we're utilizing it. I guess got to read in the next one, then free it, then read in the next one and free it. So here it goes, it's going to read and it gets the first 20. So it's actually reading that value as it's getting incremented. Okay, so something not to do, and it's pretty dangerous, is to return the address of a local static, because essentially this is a global variable. So if I have a look at that, okay, I think I might have actually shown you this before. Here I do ++i, so I start off with I being 0, then increment I, and then return the address of I. What's the issue with A and B here? Right, so essentially they're the same, right? So if I do star A or star B, I get the same memory location. So I could, here I'm abusing that. By doing star A and actually overriding the value. Can you think of a way I could actually prevent this from happening? So, ensure that this value could not be changed outside of the function. How about, yeah, exactly. So what I would do is up here, so enforce it via the function. Okay. Okay. There we go. So here, error assignment of a read-only location. And here I try to assign it to something which is not a const pointer, and it won't let me do it. So that's good. What impact? Oh yeah, I haven't really covered that here, but what impact does it have if I make a global variable static? It's only visible in the same what? File. Correct. I tried an experiment last year when I ran this course. I went, oh, here's a good idea. Why don't I make read rest of line static? I thought that was a really good idea. Really kind of enforced that people should only be calling that, well, that should only be calling it from functions which are implemented in that same file. People did all kinds of stuff because they didn't quite get that that was the requirement. And so I decided not to do that this year. But yeah, basically enforces that it can only be called inside this C file. And you should then not have, and it's only inside this C file from the point at which it is defined. So if you put it right down the bottom of the file, even the other stuff higher up in the same file can't access it. Okay? So that's one issue. Yeah. So the main thing is it should only be, it's only visible in the same file. Okay, register. Now, I would almost never use this. Because what it means and what people think it means are not the same thing. So it is a request. If you specify that something is a register storage class, so for example, register int I, right? Then this is a request to allocate a register to this variable. But often the compiler is smarter than you. The other thing is you can't take the address of a register variable. Why not? Why can't we take the address of a register variable? It may not be in memory, is the point. Because if the request for a register, if the request for a register was successful, then it's not in memory. But generally speaking, when you use the word register these days, what it really is saying to the compiler is optimize for the fastest access speed for this variable. Now the fastest access speed for this variable may in fact mean putting a different variable in a register, because then we're going to optimize on this variable in terms of caching or something else, right? Generally, compilers are a lot smarter than you and me. And unless you're an architecture specialist, you probably don't know as much as the people who made the compiler about where this should really be put. So think about it as optimize the access speed for this thing. It's really important that this be accessed as quickly as possible. Okay? That's essentially the meaning of register. Okay, compiling on different platforms. So in any programs above, the smaller, basically we get you to write really small programs at university. Even the programs for this course, which are probably some of the largest that you've written so far, are toys. I've tried to make them as close to being a complete program as possible, because I think it's kind of good for you to be able to walk out of here and be able to go, hey, look at this, I made this, and I can add these other things to it, and they are something which somebody could actually use. I think that's important. But real world programs, you probably want to implement them so that they actually work on different machines, and you probably want to know more about those machines than what you can typically with ANSI C functions. You want to use external libraries, you want to use system libraries that actually implement things which you need, right? In order to do that, you need some conditional compilation. Now, one thing that's really interesting, and I'd encourage you to have a look at the C11 standard, because there are things in the C11 standard which move away from what we're doing here, because what they do is, for example, there is a C11 threading library that works on all operating systems, and you don't need to know the details of how threads are implemented on the various operating systems. When you're using C89 or ANSI C, or you're using C99, you do need to know, because you're going to be using your own threads library. So, for example, in the Unix environment, we tend to use the pthread library. I don't really know much about the Windows threading library, but in C11, there's a single thread. There's a thread T object variable that can be used for multi-threading regardless of your operating system. But in C89, we don't have access to that, so what we do is we do something like this. So portable.c. And then we have these variables we've got defined. So hash if def underscore Linux. We're running Linux. Elif defined win32 or defined underscore win32 or defined underscore win32. These are all system defined macros, and the defined macro, the defined, that's a macro itself. So it's actually the same. So hash if define is the same as hash if def, right? And I've used defined here only because there are several in a row. So is win32 defined, or is underscore win32, or underscore win32? And why have I got this last one? What's that? Correct. So Cygwin is a Unix-like environment which you can install on Windows. And actually my office at work, I have Cygwin installed there because I just find it to be a nice environment. To then I log in from there to say the Unix servers. Yeah, I prefer doing it that way. So you see here, we can know what kind of system we're on. Based on, so here we've got Solaris system, we've got Windows, and we've got Linux. So let's see if this actually works. Encourage anyone who's running Windows to give this a go as well. So GCC NC wall pedantic okay. We're running Linux, which is exactly what I would expect. Mind you, I haven't actually tested myself because I don't have a C compiler on my Windows machine, whether the Windows works. So if you're running Windows, and say if you're using, I don't know, say MinGW or Code Blocks or Div C++, see what you get. Okay, so when you're writing real software that you has to work on a variety of different systems and so on, where you've got 29,000 source files, who thinks that that somebody actually wrote the makefile for projects that big? Now what people do is they write scripts which create the makefiles, and the scripts are a lot shorter and a lot less work than having to write a different makefile for each directory. Kind of. One tool that I've used in the past, and I reckon is pretty good, is CMake. I might see if I can open it. Okay, let me just resize that. So CMake is an open source project. We're not going to download the software. It's actually pretty easy to write you write what's called a CMake file, a CMake list.txt, and they've got reasonable documentation. There's a little tutorial, and they've got examples of executable, largely focused on C++, but can be used for C. And it writes the make files. It also writes project files for other environments. So for example, if you're using Visual Studio, it can write project files for that, or if you're using code blocks or Eclipse or whatever you might be using, CMake can be used for that. CMake I find is a bit more modern and a bit more flexible, but something which is actually, if you're going to be managing or involved with a Unix environment at all, Automake is often used to create the build system for Unix software. So let's have a quick look at that. I don't know why it's doing that. I might just have to copy and paste. Yeah. And so basically, Automate can be used to create a basically a configure script, which basically what it does is it will test whether the requirements for your system exist, and if they don't, it'll tell you what you need to download to get your system up and running so that you can actually compile this program. CMake does the same thing. I've mainly used CMake. I haven't used Automake. But you want to have professional build tools and you want them to be portable across systems. And these are examples of doing that, where you're not so much tied into your IDE, but you want to be flexible for whatever the customer is running, rather than them have to run what you want them to run. And these tools are actually one way of doing that. Okay, so that's the end of the lecture.